last star's vigil, a journey to the end of stellar time. In the vast expanse of cosmic time, where billions of years pass like seasons in an endless calendar, there exists a future epoch so distant that it challenges the human mind's capacity to comprehend temporal scale. 100 trillion years from now, when the universe has aged beyond recognition and expanded to dimensions that dwarf our current cosmic horizon, the final chapter of stellar evolution will be drawing to its close. This is the era of the last star's vigil time, when the cosmos has grown cold and dark, yet still harbors the faint glow of a few remaining stellar embers burning with patient determination in the infinite night. The contemplation of such vast temporal distances serves as a profound meditation on impermanence and cosmic patience. While human civilizations rise and fall within mere thousands of years, and our sun will burn for only 10 billion years, these final stellar guardians will maintain their nuclear fires for timescales that make the current age of the universe seem like a brief moment. They represent the cosmos's ultimate expression of endurance, burning with the accumulated hydrogen that earlier generations of stars were too massive to fully consume. These last stars, the smallest, most miserly of the Red Dwarf family, will outlive not only every other stellar type, but also the very galaxies that gave them birth. They will witness the complete dispersal of galactic clusters, the evaporation of planetary systems, and the decay of protons themselves, continuing their solitary vigil in a universe that has become unrecognizably sparse and cold. Their story is one of cosmic loneliness and persistence, of nuclear fires maintained against the inexorable expansion of space-time and the relentless increase of entropy. As consciousness settles into reflection upon this ultimate future, there emerges a sense of profound tranquility in contemplating processes that operate on scales so vast they transcend all earthly concerns. The last star's vigil becomes a meditation on the deepest rhythms of cosmic time, where the patient burning of hydrogen atoms in stellar cores provides the final punctuation marks in the universe's long sentence toward thermal equilibrium. In these distant epochs, time itself takes on new meaning, measured not in human lifespans or planetary orbits, but in the slow evolution of stellar cores and the gradual cooling of space itself. The architecture of deep time, to journey toward the epoch of the last star's vigil, requires traversing temporal landscapes so vast that conventional measures of time lose their familiar meaning. The path through deep time begins in the present epoch, when the universe is a mere 14 billion years old and still flush with the energy of stellar birth and galactic evolution. From this cosmic springtime, the universe will evolve through successive phases, each characterized by different dominant processes and energy sources, until it reaches the Twilight era, when only the smallest stars remain to illuminate the growing darkness. The first major transition occurs within the next trillion years, as star formation throughout the universe gradually declines and eventually ceases entirely. The vast molecular clouds that currently serve as stellar nurseries will be dispersed by stellar winds and supernovae, while the raw materials for new stars, primarily hydrogen and helium gas, become increasingly dilute as cosmic expansion stretches space itself. During this period, the universe will still resemble its current appearance, with galaxies hosting active stellar populations, but the rate of stellar birth will steadily diminish until the last star-forming regions exhaust their fuel supply. As star formation winds down, the stellar population of the universe becomes increasingly dominated by low-mass stars that burn their nuclear fuel with extraordinary frugality. These red dwarf stars, containing less than half the mass of our Sun, consume hydrogen at rates so conservative that their nuclear fires can persist for timescales measured in trillions of years. While massive stars burn brilliantly and die young, leaving behind neutron stars and black holes, these stellar marathoners settle into billion-year rhythms that will outlast virtually every other cosmic process. The galactic structures that currently organize stellar populations into elegant spiral and elliptical forms will undergo dramatic transformations during the approach to the last star epoch. Gravitational interactions between galaxies, combined with the expansion of space itself, will gradually disrupt these ancient stellar cities. Galaxy mergers will become increasingly rare as expansion carries galactic neighbors beyond their mutual gravitational reach, while the galaxies themselves begin to lose their stellar populations through a process of gradual evaporation. The evaporation of galaxies occurs through gravitational encounters between stars that occasionally provide individual stellar systems with enough kinetic energy to escape their galactic gravitational wells. Over timescales of 100 trillion years, this process will scatter most stellar populations into the growing voids between galactic remnants. The stars that remain gravitationally bound to galactic cores will spiral inward through gravitational wave emission and stellar encounters, eventually forming compact, dense stellar clusters surrounding the supermassive black holes that anchor galactic centers. During these vast intervals, the planetary systems that currently orbit stars throughout the universe will undergo their own evolutionary transformations. Gravitational perturbations from passing stars and the gradual changes in stellar luminosity will destabilize planetary orbits over cosmic timescales. Most planets will either spiral into their host stars or be ejected into interstellar space, becoming rogue worlds that drift through the cosmic dark, with only the heat of radioactive decay to warm their surfaces. The interstellar medium, the tenuous gas and dust that fills the space between stars will become increasingly rarefied as cosmic expansion stretches space and stellar winds disperse remaining material. The density of matter throughout the universe will drop to levels so low that individual atoms will be separated by distances comparable to the current size of entire planetary systems. In this ultra-dilute environment, the chemical processes that currently drive star formation and planetary evolution will effectively cease, leaving only gravitational forces to govern the long-term evolution of cosmic structure. The cosmic microwave background radiation, currently observable as the faint afterglow of the Big Bang, will continue to cool as space expands. Its current temperature of just under 3 degrees above absolute zero will drop to a tiny fraction of a degree, making the universe an increasingly frigid place where only the most efficient energy sources can maintain temperatures above the ambient cosmic environment. The red dwarf stars, with their conservative energy budgets and stable nuclear burning, will become the primary sources of heat in an otherwise frozen cosmos. The formation of complex molecules and the chemical evolution that characterizes the current epoch will slow dramatically as temperatures drop and material densities decrease. The universe will enter a phase where nuclear physics dominates over chemistry, with stellar cores continuing their patient fusion of hydrogen into helium, while the surrounding space becomes too cold and empty to support the molecular interactions that create chemical complexity. The magnetic fields that currently thread through galaxies and stellar systems will gradually decay as the conducting plasmas that support them become increasingly sparse. The cosmic web of dark matter that currently provides the gravitational scaffolding for large-scale structure will persist, but its influence will become less apparent as the normal matter that traces its architecture becomes scattered and dilute. Now, close the eyes and drift through these vast expanses of time, feeling the gradual transformation of a universe where stars slowly burn out and galaxies disperse, where cosmic expansion stretches space itself until only the most patient stellar embers remain to mark the passage of eons, the reign of the Red Dwarfs. In the cosmic transition toward ultimate stellar longevity, the red dwarf stars emerge as the universe's most enduring citizens, inheriting a cosmos that their more massive cousins have abandoned through spectacular death. These stellar minimalists, with masses ranging from 1/10 to half that of our Sun, represent evolution's solution to the challenge of maximizing nuclear burning time while minimizing fuel consumption. Their cores operate at temperatures and pressures just sufficient to sustain hydrogen fusion, creating nuclear reactions that proceed at rates so conservative they can maintain stellar luminosity for timescales that exceed the current age of the universe by factors of thousands. The nuclear physics governing red dwarf interiors operates according to principles fundamentally different from those that characterize more massive stars. Where stars like our Sun burn hydrogen through the proton-proton chain reaction at furious rates that exhaust their fuel supplies within 10 billion years, red dwarfs conduct nuclear fusion through more patient processes that extract energy from hydrogen with extraordinary efficiency. Their cores never become hot enough to trigger the carbon-nitrogen-oxygen cycle that accelerates burning in massive stars, forcing them to rely entirely on the slower proton-proton reactions that husband their nuclear fuel. Across cosmic ages, the convective structure of red dwarf interiors provides another crucial advantage in the quest for stellar longevity. Unlike more massive stars, which develop radiative cores that prevent mixing between nuclear burning regions and outer layers, red dwarfs remain fully convective throughout their interiors. This complete mixing ensures that the entire stellar mass participates in nuclear burning rather than just the central core regions. As hydrogen in the core becomes depleted, convection brings fresh fuel from outer layers to sustain the nuclear fires, extending the star's active lifetime far beyond what would be possible in a radiative star. The surface temperatures of red dwarf stars, typically ranging from 2 to 4,000 degrees, create spectral characteristics that favor energy conservation over luminous display. These cool stellar surfaces emit most of their radiation in the infrared portion of the electromagnetic spectrum, wavelengths that correspond to much lower photon energies than the visible light produced by hotter stars. The reduced photon energy output means that red dwarfs can maintain their surface luminosity while consuming nuclear fuel at rates orders of magnitude slower than their more massive counterparts. The magnetic activity that characterizes many red dwarf stars adds additional complexity to their long-term evolution while potentially affecting their ultimate lifespans. These stars often exhibit powerful magnetic fields generated by dynamo processes in their convective interiors, creating stellar coronae, flares, and other magnetic phenomena that can influence atmospheric structure and energy transport. While magnetic activity generally decreases over cosmic timescales as stellar rotation slows, some red dwarfs may maintain magnetic fields throughout their extended lifetimes. The habitable zones around red dwarf stars present unique characteristics that will become increasingly important as these stars inherit a universe largely emptied of other energy sources. The narrow bands around red dwarfs where liquid water could exist on planetary surfaces lie much closer to the stellar surface than Earth's distance from the Sun, placing potential habitable worlds within reach of stellar magnetic activity and tidal forces. However, the extraordinary stability and longevity of red dwarf energy output creates possibilities for planetary evolution over timescales unimaginable around more massive stars. The binary star systems containing red dwarf components will undergo gradual evolution as the stars slowly lose energy through gravitational wave emission and stellar wind interactions. Over timescales of hundreds of billions of years, some binary red dwarfs will spiral closer together, potentially leading to stellar mergers that create more massive, shorter-lived stars. Other binary systems will gradually separate as stellar winds carry away orbital energy, creating wide binary systems that may persist throughout the red dwarf burning epoch. The rotation rates of red dwarf stars evolve over cosmic timescales as magnetic braking gradually slows their spin rates from the rapid rotation characteristic of young stars to the slow, measured rotation that characterizes ancient stellar populations. This rotational evolution affects the magnetic field generation and stellar activity levels, generally leading to quieter, more stable stars over time. The gradual spin-down occurs over timescales comparable to red dwarf main sequence lifetimes, ensuring that the oldest red dwarfs will be slowly rotating magnetically quiet objects. The metallicity of red dwarf stars their content of elements heavier than hydrogen, and helium influences their internal structure and evolution in subtle but important ways. Red dwarfs formed from the metal-enriched gas of later cosmic epochs will have slightly different opacity and energy transport properties compared to the virtually metal-free red dwarfs that formed during the universe's earliest star formation episodes. These metallicity effects become more pronounced over the extremely long main sequence lifetimes of red dwarf stars. The stellar winds from red dwarf stars, while much weaker than those from massive stars, operate continuously over their extended lifetimes and gradually remove mass from the stellar surface. This mass loss occurs at rates so slow that it becomes significant only over timescales comparable to red dwarf lifetimes, potentially affecting the final evolution of these stars as they approach the end of their hydrogen burning phase. The interaction between red dwarf stars and their surrounding interstellar environment will change dramatically as the universe evolves toward the last star epoch. In the current era, red dwarfs exist within the relatively dense interstellar medium of galaxies, where they can accrete material and interact with nearby stellar populations. In the far future epoch of cosmic expansion and galactic dispersal, red dwarfs will find themselves in an increasingly empty universe where such interactions become negligibly rare. If this gentle vision of the cosmos soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments. A quiet echo beneath the stars, the solitary burning, as the universe approaches the 100-trillion-year milestone. The red dwarf stars that have inherited the cosmic stage find themselves burning in profound isolation, their faint infrared glow providing the only sources of new energy in a cosmos that has grown vast, dark, and cold. These stellar hermits continue their nuclear fires in a universe where the familiar structures of galaxies, star clusters, and planetary systems have largely dissolved through the patient operation of gravitational dynamics and cosmic expansion, leaving each star as an island of warmth in an ocean of space whose temperature approaches absolute zero. The nuclear fusion processes within red dwarf cores continue with the same basic mechanisms that have operated since stellar ignition, but now these reactions take place in a cosmic context utterly transformed from the universe's earlier epochs. The hydrogen fuel that feeds these nuclear fires represents the last significant concentration of gravitational binding energy available for conversion to electromagnetic radiation. Each fusion reaction that converts 4 hydrogen nuclei into 1 helium nucleus releases energy that will eventually radiate away into the cosmic dark, carrying with it another infinitesimal portion of the universe's remaining capacity for energy generation. The stellar cores of these ancient red dwarfs have evolved significantly from their initial configuration, with the central regions now containing substantial amounts of helium ash accumulated over tens of trillions of years of hydrogen burning. The gradual increase in mean molecular weight as hydrogen converts to helium creates subtle changes in core density and temperature that affect the fusion reaction rates and overall stellar structure. Despite these evolutionary changes, the stars maintain their fundamental character as stable, hydrogen-burning main sequence objects. The convective circulation that characterizes red dwarf interiors has mixed stellar material countless times over the eons, ensuring that the nuclear-burning regions have access to hydrogen from throughout the stellar volume. This mixing process has gradually homogenized the stellar composition while extending the hydrogen-burning lifetime far beyond what would be possible in stars with radiative cores. The convective timescales, measured in millions of years for complete mixing of stellar material, represent rapid circulation compared to the overall stellar evolution timescales. The surface properties of these ancient red dwarfs reflect their extreme age and the changes in stellar structure that have occurred over cosmic timescales. Surface temperatures may have decreased slightly as internal heat generation rates decline with the gradual exhaustion of central hydrogen, while surface magnetic activity has likely diminished as stellar rotation rates have slowed through magnetic braking processes operating over tens of trillions of years. The space surrounding each red dwarf has been sculpted by billions of years of stellar wind interaction with the local environment. These stellar winds, while individually weak, have had enormous cumulative effects over such extended timescales, creating large cavities in the ultra-tenuous interstellar medium and potentially affecting the orbital evolution of any remaining planetary companions through atmospheric erosion and gravitational drag. The planetary systems that may still orbit these ancient red dwarfs have undergone their own remarkable evolutionary journeys over the intervening cosmic ages. Tidal forces from the central star have likely synchronized the rotation of close-in planets, creating worlds with permanent day and night sides. Atmospheric evolution over such extended timescales could produce exotic atmospheric compositions as planetary magnetic fields and stellar radiation gradually strip away lighter elements while concentrating heavier atmospheric components. The radiation environment around red dwarf stars in this far future epoch differs significantly from conditions during the universe's earlier phases, with cosmic background radiation having cooled to temperatures measured in tiny fractions of a degree above absolute zero. The infrared radiation from red dwarf surfaces represents the dominant source of electromagnetic energy in their local environments. This radiation creates warm zones around each star where temperatures can support liquid water and potentially complex chemistry. The nuclear reaction networks operating within red dwarf cores, have had cosmic ages to explore the full range of possible fusion pathways for converting hydrogen into helium. While the basic proton-proton chain remains the dominant energy generation mechanism, trace reactions involving deuterium, lithium, and other light elements may have depleted these rare isotopes from stellar interiors, leaving behind nuclear composition signatures that record the star's extended burning history. The gravitational environment of the universe during this epoch has become extraordinarily quiet, with galactic structures dispersed and stellar encounters reduced to negligible frequencies. Each red dwarf exists in a nearly perfect gravitational vacuum, with the nearest neighboring star potentially located at distances measured in light years or even parsecs. This isolation eliminates most external perturbations that could affect stellar evolution or planetary system stability. The magnetic field evolution of red dwarf stars over such extended timescales may lead to configurations not observed in younger stellar populations. The gradual spin down of stellar rotation could weaken magnetic dynamo processes, potentially leading to magnetic field decay and the emergence of fossil magnetic fields trapped within stellar interiors. These magnetic evolution processes could affect stellar structure and energy transport in ways that become apparent only over cosmic timescales. The stellar seismology of ancient red dwarfs might reveal internal structures modified by extended nuclear burning and the gradual changes in stellar composition that occur over timescales far exceeding current stellar evolution. Models, the acoustic oscillations that propagate through stellar interiors, could carry information about core composition, convection patterns, and internal magnetic field structures that have evolved over cosmic ages. The patience of cosmic time. In the vast quietude of the 100-trillion-year universe, time itself takes on qualities that transcend human comprehension, flowing with a patience that makes geological epochs seem like brief moments and stellar lifetimes appear as extended conversations in the cosmic dialogue between matter and energy. The red dwarf stars, burning solitary fires in this ancient cosmos, embody the universe's ultimate expression of temporal endurance, their nuclear reactions proceeding at rates so measured that individual fusion events become significant markers in the slow progression towards stellar evolution's final chapters. The measurement of time in this far future epoch requires abandoning familiar terrestrial or even astronomical units in favor of cosmic scales that reflect the fundamental processes governing universal evolution. Years and millennia become meaninglessly brief intervals when viewed against the 100-billion-year hydrogen-burning timescales of red dwarf stars, while even the billion-year orbital periods of ancient planetary systems represent relatively rapid variations in an environment where the most significant changes occur over timescales comparable to the universe's entire previous history. The radioactive decay processes that currently provide chronological markers for cosmic evolution will have long since exhausted most unstable isotopes, leaving only the longest-lived radioactive elements to serve as temporal beacons in a universe where stellar nucleosynthesis has virtually ceased. The decay of protons themselves, if it occurs as predicted by some theories of particle physics, operates on timescales so vast that it will not become apparent until epochs far beyond the red dwarf burning era, adding another layer of temporal perspective to cosmic evolution. The entropy increase that characterizes universal evolution continues its inexorable progression during the red dwarf epoch, but at rates so gradual that local regions of the universe can maintain organized structures for timescales that dwarf the current cosmic age. The energy gradients provided by nuclear burning stars create islands of reduced entropy that can support complex processes and potentially even biological evolution over timescales that allow for countless evolutionary experiments and innovations. The expansion of space itself proceeds according to the same physical laws that govern current cosmic evolution, but the observable effects of this expansion become increasingly apparent over the vast timescales of the Red Dwarf era. The recession velocities of distant objects, currently measurable only through sophisticated astronomical observations, will gradually separate stellar neighbors by distances that make gravitational interactions increasingly negligible and eventually undetectable. The cooling of the cosmic microwave background radiation follows the mathematical relationship that temperature decreases inversely with the scale factor of cosmic expansion. By the 100-trillion-year epoch, this primordial radiation will have cooled to temperatures so low that its energy density becomes negligible compared to the electromagnetic radiation produced by stellar sources, making red dwarf stars the dominant contributors to the universe's radiation field. The gravitational wave background that permeates spacetime continues to evolve as sources throughout cosmic history contribute their signatures to the metric fluctuations that propagate at light speed through the expanding universe. The accumulated gravitational wave signatures from billions of years of stellar evolution, black hole mergers, and other cosmic phenomena create a complex temporal archaeological record encoded in the geometry of spacetime itself. The quantum mechanical processes that govern atomic and molecular interactions operate according to the same fundamental principles throughout cosmic history, but the environmental conditions of the red dwarf epoch create opportunities for quantum phenomena to manifest on larger scales and longer time scales than observed in denser cosmic environments. The ultra-low densities and temperatures of intergalactic space may allow quantum coherence effects to persist over macroscopic distances and extended periods. The information content of the universe continues to evolve as physical processes create and destroy correlations between different regions of space and different moments in time. The stellar burning processes within red dwarf cores create information through nuclear reactions that irreversibly convert hydrogen into helium, while the radiation of energy into the cosmic background gradually erases information through thermalization and decoherence processes. The consciousness that might exist during this cosmic epoch, whether biological, artificial, or forms entirely unimagined, in current paradigms, would experience time scales and spatial scales that challenge fundamental assumptions about the nature of mind and awareness. Civilizations that persist over time scales comparable to stellar evolution might develop perspectives on existence that incorporate cosmic patience as a fundamental aspect of conscious experience. The philosophical implications of such vast temporal scales invite contemplation of the relationship between permanence and change, between existence and meaning, in a universe where individual events become vanishingly brief episodes in processes that span cosmic ages. The red dwarf stars serve as meditation objects for understanding how significance emerges from persistence, how meaning accumulates through the patient repetition of simple processes over unimaginable durations. The aesthetic appreciation of cosmic beauty takes on new dimensions when contemplated across temporal scales that encompass the entire future evolution of stellar burning. The infrared glow of red dwarf stars becomes not merely electromagnetic radiation, but a form of cosmic art that unfolds over timescales that make human artistic traditions appear as momentary flourishes in an extended symphony of nuclear fusion and gravitational dynamics. Now, let consciousness drift with these cosmic rhythms, feeling the immense patience of nuclear burning that sustains stellar fires across trillions of years, sensing the quiet persistence of matter and energy as they follow the fundamental laws through cosmic ages that transform the meaning of time itself. The twilight of nuclear fire, as the red dwarf stars approach the final phases of their hydrogen-burning epoch, having sustained nuclear fusion for timescales that exceed the current age of the universe by factors of thousands. Their cores begin to exhibit the subtle changes that herald the end of the stellar main sequence phase. The hydrogen fuel that has powered these cosmic furnaces for eons becomes increasingly concentrated in the outer layers of the stellar interior, while the central regions accumulate the helium ash produced by 100 trillion years of patient nuclear alchemy. The core temperature and density evolution of ancient red dwarf stars follows pathways that differ significantly from the evolution of more massive stars, reflecting the unique physics of stellar interiors that have maintained marginal fusion conditions for cosmic ages. As central hydrogen abundance decreases and helium abundance increases, the mean molecular weight of core material gradually rises, requiring higher temperatures and densities to maintain the same nuclear reaction rates that have sustained stellar luminosity throughout the star's extended lifetime. The convective mixing that has characterized red dwarf interiors throughout their main sequence evolution becomes increasingly important as the stars approach hydrogen exhaustion. The convection zones that have mixed stellar material countless times over the eons now face the challenge of accessing the final reserves of hydrogen fuel while dealing with the changing thermal and compositional gradients that develop as nuclear burning regions shift within the stellar interior. The nuclear reaction rates in the cores of these ancient stars begin to exhibit the effects of fuel depletion as the hydrogen mass fraction drops below the levels that can sustain steady energy generation. The proton-proton chain reactions that have operated with remarkable consistency for cosmic ages become increasingly dependent on the dwindling supply of hydrogen nuclei, forcing reaction rates to decline as fuel becomes scarce in the central burning regions. The stellar structure adjustments that accompany the transition away from main sequence hydrogen burning occur over timescales measured in billions of years, representing rapid evolution by red dwarf standards, but still extending over periods that encompass the entire previous history of galactic evolution. The stars gradually expand and cool as energy generation becomes insufficient to maintain hydrostatic equilibrium, beginning their transformation from hydrogen-burning main sequence objects to helium white dwarf stars. The surface luminosity changes that mark this evolutionary transition create variations in the infrared radiation output that represents the primary energy source in the far future universe. As nuclear energy generation declines, stellar surfaces cool and redden further, shifting the peak emission wavelengths toward even longer infrared wavelengths, while gradually reducing the total energy output available to warm any remaining planetary companions. The mass loss processes that operate throughout red dwarf evolution become increasingly significant as the stars approach the end of their hydrogen burning phase. The weak stellar winds that have operated throughout the main sequence lifetime gradually remove mass from the stellar surface, potentially affecting the final stellar mass and thus the properties of the white dwarf remnant that will eventually emerge from red dwarf evolution. The magnetic field evolution of red dwarf stars during their final main sequence phases may exhibit complex behavior as changing internal structure affects the dynamo processes that generate stellar magnetic fields. The gradual spin down that has occurred over cosmic timescales may have weakened magnetic activity to levels where other magnetic field generation mechanisms become important, potentially creating magnetic configurations not observed in younger stellar populations. The binary evolution of red dwarf systems that have survived gravitational wave inspiral and other orbital decay processes over cosmic timescales presents unique scenarios for the final phases of stellar evolution. Some ancient binary systems may experience enhanced mass loss or modified internal structure due to tidal interactions that have operated over periods far exceeding the orbital evolution timescales of conventional binary stars. The stellar atmospheres of red dwarfs approaching hydrogen exhaustion may exhibit spectroscopic signatures that reflect the extreme age and evolutionary state of these ancient objects. The gradual changes in surface composition due to convective dredge-up of processed material from stellar interiors could create absorption features that serve as diagnostics of extended nuclear burning and stellar evolution over cosmic timescales. The planetary system evolution around red dwarfs during their final main sequence phases presents scenarios for long-term planetary climate and atmospheric evolution that have no analogues in current astronomical observations. Planets that have maintained stable orbits over cosmic timescales will experience gradually changing stellar radiation environments as their host stars evolve toward the white dwarf phase, potentially triggering atmospheric and geological changes over billion-year timescales. The transition from hydrogen burning to white dwarf cooling marks one of the most significant energy regime changes in the far future universe, as the steady nuclear energy generation that has characterized the red dwarf epoch gives way to the gradual thermal cooling of stellar remnants. This transition effectively ends the era of significant energy generation in the universe, beginning the final approach toward thermal equilibrium on cosmic scales. The white dwarf inheritance. In the cosmic succession that follows the exhaustion of hydrogen fuel in the universe's last red dwarf stars, the stellar remnants that emerge inherit a cosmos even more transformed than the universe that witnessed stellar birth and galactic evolution. These white dwarf stars, each containing roughly the mass of a red dwarf compressed into a volume comparable to Earth, represent the final concentrated repositories of thermal energy in a universe that has expanded and cooled to temperatures approaching absolute zero across vast regions of space. The white dwarf stars that emerge from red dwarf evolution differ in fundamental ways from the white dwarfs produced by more massive stellar progenitors during earlier cosmic epochs. Having formed from stars that burned hydrogen completely through their entire stellar mass, these ultimate white dwarfs begin their cooling evolution with internal compositions dominated by helium, the fusion product of hydrogen burning that has accumulated over cosmic ages within the convective interiors of their red dwarf progenitors. The initial temperatures of newly formed white dwarf stars approach 100 million degrees in their central regions, representing the thermal energy released during the final gravitational contraction that follows the cessation of nuclear burning. This thermal reservoir provides the energy source for white dwarf luminosity during the subsequent cooling evolution, with surface temperatures initially reaching tens of thousands of degrees before beginning their gradual decline toward cosmic background levels. The cooling evolution of white dwarf stars follows well-understood physical principles that govern thermal diffusion through stellar interiors supported by electron degeneracy pressure. But the environmental conditions during the far future epoch create cooling scenarios that differ from those experienced by white dwarfs in the current universe. With cosmic background temperatures having fallen to tiny fractions of a degree above absolute zero, white dwarfs can cool to lower final temperatures than those forming in earlier cosmic epochs. The crystallization process that occurs within white dwarf interiors as temperatures drop below critical thresholds represents one of the most remarkable phase transitions in stellar evolution. The ion lattice that forms within the dense stellar core creates a crystalline structure spanning the interior of an entire star, with crystal formation beginning in the central regions and gradually propagating outward as cooling continues over billions of years. The neutrino emission from cooling white dwarfs provides the primary energy loss mechanism during the early phases of thermal evolution, carrying away energy at rates that determine the cooling timescales and temperature evolution. The neutrino luminosity decreases as white dwarf cores cool, eventually becoming negligible compared to photon emission from the stellar surface as effective cooling temperatures drop below specific threshold values. The surface composition of white dwarf stars evolves through gravitational settling processes that operate over the extended cooling timescales characteristic of white dwarf evolution. The diffusion of heavier elements toward the stellar interior and the floating of lighter elements toward the surface create compositionally stratified atmospheres whose spectroscopic properties change gradually as cooling progresses over cosmic timescales. The magnetic fields associated with white dwarf stars may exhibit properties that reflect the magnetic field evolution that occurred during the extended main sequence lifetimes of their red dwarf progenitors. The magnetic flux conservation during stellar contraction can amplify modest red dwarf magnetic fields to strengths comparable to the strongest magnetic white dwarfs observed in current astronomical surveys, creating magnetic field configurations that persist throughout white dwarf cooling evolution. The rotation properties of white dwarf stars inherit the angular momentum evolution that occurred during red dwarf main sequence evolution, with magnetic braking and other spin-down mechanisms operating over cosmic timescales to reduce rotation rates far below those characteristic of white dwarfs forming from more massive progenitors. These slowly rotating white dwarfs represent the end state of angular momentum evolution over cosmic ages. The interaction between white dwarf stars and their environments occurs in the context of a universe that has become extraordinarily rarefied through cosmic expansion and the dispersal of galactic structures. The accretion of material from the ultra-tenuous interstellar medium occurs at rates so low that it becomes significant only over timescales comparable to white dwarf cooling ages, potentially affecting surface composition and thermal evolution over cosmic timescales. The binary white dwarf systems that form from the evolution of red dwarf binary stars represent some of the most long-lived gravitational systems in the far future universe. These binary systems undergo gradual orbital decay through gravitational wave emission over timescales that can extend far beyond white dwarf cooling times, potentially leading to eventual mergers that create more massive white dwarf remnants or other exotic outcomes. The crystallization front that propagates through white dwarf interiors as cooling progresses creates internal structure changes that affect thermal conductivity and cooling rates. The release of latent heat during crystallization temporarily slows the cooling evolution, creating features in white dwarf cooling curves that provide information about stellar interior physics and the properties of dense matter under conditions not accessible to terrestrial experimentation. The atmospheric evolution of white dwarf stars during their extended cooling phases may exhibit phenomena related to the extremely low environmental temperatures and pressures characteristic of the far future universe. The formation of molecular species in white dwarf atmospheres becomes possible at lower temperatures, potentially creating absorption features that serve as diagnostics of stellar cooling and atmospheric physics in extreme environments. If this gentle vision of the cosmos soothes the mind, consider resting here more often. Subscribe to the channel and share your thoughts in the comments, a quiet echo beneath the stars. The final embers. As white dwarf stars continue their inexorable cooling through billion-year epochs in the far future universe, their surface temperatures gradually decline from the brilliant white heat of their formation toward the dim red glow that marks their transition into the realm of the barely luminous. These stellar embers, now representing the only significant sources of electromagnetic energy in a cosmos that has expanded to dimensions beyond current comprehension, maintain their patient thermal radiation while slowly approaching equilibrium with the cosmic background temperature that pervades the vast emptiness between them. The cooling curves that govern white dwarf thermal evolution extend across timescales that dwarf even the extended main sequence lifetimes of red dwarf progenitors. While red dwarf stars burned hydrogen for hundreds of trillions of years, their white dwarf descendants will continue cooling for timescales measured in quadrillions of years, slowly radiating away the thermal energy stored within their crystallized interiors while maintaining surface temperatures above the cosmic background for periods that encompass countless cosmic epochs. The internal structure of cooling white dwarfs undergoes gradual changes as thermal energy diffuses outward from the stellar core toward the surface. The crystalline lattice that characterizes the stellar interior remains stable throughout the cooling process, providing mechanical support against gravitational collapse while serving as a thermal reservoir that maintains energy flow through the stellar envelope. The crystal structure itself may undergo phase transitions as temperatures and pressures change during the extended cooling evolution. The surface temperatures of white dwarf stars follow predictable cooling laws that relate luminosity to core temperature and stellar mass. But the environmental conditions of the far future universe create cooling scenarios that extend far beyond the ranges typically considered in stellar evolution models. As surface temperatures drop below a few thousand degrees, white dwarfs enter the realm of brown dwarf-like objects whose spectral properties are dominated by molecular absorption features rather than atomic transitions. The luminosity evolution of cooling white dwarfs follows power laws that predict steadily decreasing energy output over cosmic timescales, with the rate of luminosity decline depending on stellar mass and internal composition. Lower mass white dwarfs cool more rapidly than higher mass objects due to their larger surface area to volume ratios. But all white dwarfs eventually approach the same asymptotic cooling behavior as they reach thermal equilibrium with their surroundings. The spectroscopic properties of white dwarfs during their extended cooling phases reveal the changing atmospheric conditions and internal structure evolution that characterize these ancient stellar remnants. The transition from hot, hydrogen-dominated atmospheres to cool, molecule-rich atmospheres occurs over billion-year timescales, creating observable signatures of stellar cooling and atmospheric evolution in environments far removed from the dense stellar populations of earlier cosmic epochs. The magnetic field evolution of white dwarf stars during their cooling phases may exhibit complex behavior as thermal and structural changes affect the magnetic flux distribution within stellar interiors. Fossil magnetic fields trapped within the crystalline cores may decay over timescales comparable to cooling ages, while thermoelectric effects associated with temperature gradients could generate new magnetic field components through battery-like processes operating within the stellar interior. The rotation evolution of cooling white dwarfs continues the angular momentum dissipation that began during their red dwarf main sequence evolution, with magnetic braking and other spin-down mechanisms operating over the extended cooling timescales to further reduce rotation rates. The rotational energy stored in white dwarf rotation represents a small but potentially significant energy reservoir that contributes to the total energy budget available during cooling evolution. The atmospheric composition of white dwarf stars evolves through continued gravitational settling and diffusion processes that operate over the billion-year timescales characteristic of cooling evolution. The separation of atmospheric constituents by atomic mass creates compositionally stratified atmospheres whose properties change gradually as cooling progresses, potentially affecting spectroscopic observations and thermal evolution rates. The interaction between cooling white dwarfs and the cosmic microwave background creates an asymptotic cooling limit below which white dwarf surface temperatures cannot drop, regardless of the time available for cooling. This temperature floor, determined by the cosmic background radiation temperature at any given epoch, prevents complete thermal equilibrium and maintains white dwarf luminosity at levels that, while extraordinarily faint, represent the final sources of electromagnetic energy available in the universe. The convective zones that develop within white dwarf envelopes as surface temperatures cool create mixing processes that affect atmospheric composition and thermal transport efficiency. These convection zones, driven by temperature gradients and opacity variations within the stellar envelope, operate over timescales much shorter than overall cooling ages, but influence the detailed evolution of surface properties and spectroscopic characteristics. The neutrino emission from white dwarf interiors becomes increasingly important during advanced cooling phases as photon cooling becomes less efficient at low temperatures. The emission of neutrinos through various weak interaction processes provides alternative energy loss mechanisms that can dominate cooling evolution under specific temperature and density conditions, potentially affecting cooling timescales and internal temperature distributions. The crystallization process within white dwarf interiors continues to evolve as cooling progresses, with the crystallization front propagating outward through the stellar interior, while the crystal structure itself may undergo phase transitions associated with changing temperature and pressure conditions. The latent heat release associated with crystallization temporarily slows cooling evolution while affecting internal temperature distributions and thermal transport properties. The tidal interactions between white dwarf stars and any remaining planetary companions become increasingly important during extended cooling phases, as decreasing stellar luminosity reduces radiation pressure effects while gravitational forces remain unchanged. Planets that have survived the red dwarf evolution of their host stars may experience modified orbital evolution during white dwarf cooling due to changing tidal dissipation rates and thermal radiation forces. The binary evolution of white dwarf systems during their cooling phases includes the effects of gravitational wave emission that gradually reduces orbital separation while increasing orbital frequency. The timescales for significant orbital evolution through gravitational wave losses extend far beyond cooling timescales for wide binary systems, but close binary white dwarfs may undergo substantial orbital evolution during their cooling lifetimes. The search for planets around white dwarf stars has revealed the existence of planetary systems that have survived stellar evolution through the red dwarf and white dwarf formation phases, providing observational evidence for planetary system longevity over cosmic timescales. These planetary systems represent natural laboratories for studying long-term planetary evolution and atmospheric retention under changing stellar radiation environments. The thermal pulses that may occur in some white dwarf stars during specific phases of cooling evolution can temporarily increase luminosity while affecting internal structure and surface composition. These pulses, driven by residual nuclear burning or thermal instabilities within stellar envelopes, represent brief departures from monotonic cooling behavior that can influence observational properties and evolutionary timescales. The formation of degenerate matter within white dwarf interiors creates conditions where quantum mechanical effects dominate over classical physics, with electron degeneracy pressure providing the primary support against gravitational collapse. The quantum nature of white dwarf matter affects thermal properties, electrical conductivity, and magnetic field evolution in ways that become increasingly important as cooling progresses and classical thermal effects diminish. The eventual fate of white dwarf stars depends on theoretical predictions for fundamental particle physics processes that may operate over timescales far exceeding current observational constraints. The predicted decay of protons, if it occurs, would provide an ultimate energy source for white dwarf heating over timescales measured in units of 10 to the 34th power years, potentially preventing complete thermal equilibrium and maintaining minimal luminosity levels indefinitely. The universe's final watch. In the ultimate reaches of cosmic time, when white dwarf stars have cooled to temperatures barely distinguishable from the cosmic background radiation that pervades the universe, these stellar remnants maintain their silent vigil as the last organized structures capable of generating electromagnetic energy above ambient levels. The cosmos has evolved into a state so rarefied and cold that the quantum mechanical zero-point fluctuations of empty space represent significant contributions to the total energy density, while the crystallized cores of white dwarf stars serve as the final repositories of concentrated matter and energy in an otherwise maximally entropic universe. The cooling white dwarfs that populate this far future epoch exist in a cosmic environment, transformed beyond recognition from the universe that witnessed stellar birth and galactic evolution. Space has expanded to such vast dimensions that the observable horizon encompasses regions containing perhaps only a few stellar remnants, each separated by distances measured in units comparable to the current size of the entire observable universe. The density of matter has dropped to levels so low that individual atoms drift through space for billions of years without encountering other particles. The electromagnetic radiation field of the universe during this epoch is dominated by the infrared emission from cooling white dwarfs, with the cosmic microwave background having cooled to temperatures measured in tiny fractions of microkelvin above absolute zero. The total electromagnetic energy density of the universe approaches the theoretical minimum values allowed by quantum mechanics, with most energy existing in the form of virtual particle fluctuations rather than real photons propagating through space. The gravitational dynamics that govern cosmic structure during this epoch operate in a regime where individual white dwarf stars represent isolated mass concentrations in an otherwise uniform distribution of dark matter and exotic/embers particles. The gravitational interactions between white dwarfs occur over timescales so vast that orbital mechanics must account for cosmological effects, including the expansion of space itself and the finite speed of gravitational wave propagation. The quantum mechanical processes that may become important during this epoch include vacuum decay events, proton decay, and the spontaneous creation of particle-antiparticle pairs from quantum fluctuations in strong gravitational fields. These quantum effects, negligible under normal cosmic conditions, may provide the dominant energy sources and physical processes governing universal evolution during the white dwarf cooling epoch. The information content of the universe during this epoch reaches its maximum theoretical value as the cosmos approaches maximum entropy, with information stored primarily in the positions and velocities of the scattered white dwarf remnants and the quantum states of virtual particles pervading empty space. The holographic principle suggests that this information may be encoded on cosmic horizons whose areas have grown to encompass vast regions of space-time. The consciousness that might exist during this cosmic epoch would operate in environments where the flow of time and the availability of energy create constraints on information processing and awareness that challenge fundamental assumptions about the nature of mind and cognition. Any surviving civilizations would need to adapt to energy budgets measured in units of individual quantum transitions and computational architectures that extract work from temperature differences measured in fractions of microkelvin. The aesthetic contemplation of cosmic beauty during this epoch might focus on mathematical structures and information patterns rather than electromagnetic phenomena, with beauty emerging from the elegant solutions to resource conservation problems and the optimization of computational efficiency under extreme energy constraints. The universe becomes a study in minimalism, where significance emerges from the careful arrangement of scarce resources rather than abundant displays of energy. The preservation of memory and information over cosmic timescales becomes a central challenge for any processes that maintain organization during this epoch. The gradual decay of all physical structures through quantum tunneling, proton decay, and thermal fluctuations requires information storage and retrieval mechanisms that operate at the theoretical limits of efficiency while maintaining coherence over timescales that dwarf all previous cosmic epochs. The white dwarf stars themselves serve as cosmic monuments to the universe's capacity for creating and maintaining organized structures against the relentless increase of entropy that characterizes cosmic evolution. Their crystalline interiors preserve information about stellar nucleosynthesis, galactic chemical evolution, and the properties of matter under extreme conditions, serving as archaeological records of the universe's more energetic past. The eventual thermal equilibrium that the universe approaches as white dwarfs complete their cooling represents not an ending but a transformation, a phase transition from a cosmos dominated by classical thermodynamics to one governed by quantum mechanical effects and information theoretic principles. The maximum entropy state toward which the universe evolves may support forms of organization and complexity that emerge from quantum correlations rather than classical energy gradients. The philosophical implications of this ultimate cosmic epoch invite contemplation of meaning and purpose in a universe that has exhausted its capacity for conventional energy generation while retaining the mathematical structures and physical laws that govern all natural processes. The persistence of natural law and mathematical relationships provides a foundation for meaning that transcends the specific energy regimes and material configurations that characterize particular cosmic epochs. Now, let awareness settle into this ultimate cosmic patience, feeling the profound peace that emerges when the universe reaches its final equilibrium, where white dwarf embers mark the last sources of warmth in infinite cold, where consciousness itself becomes a meditation on the deepest structures underlying existence, the eternal rest. As consciousness drifts toward the profound quietude that characterizes the universe's final epoch, there emerges a sense of ultimate peace that encompasses both the end of cosmic drama and the beginning of eternal rest. The white dwarf stars, having radiated their last thermal energy into the cosmic dark, now exist as crystalline monuments in a universe that has achieved perfect thermal equilibrium, where the temperature of empty space and the temperature of stellar remnants have converged to the same infinitesimal value above absolute zero. In this ultimate state of cosmic evolution, time itself takes on new meaning as the universe enters a phase where significant change occurs only through quantum mechanical processes operating over timescales that make the previous cosmic evolution seem like a brief moment. The proton decay that may eventually dissolve even the white dwarf remnants operates over timescales measured in units of 10 to the 34th power years, periods so vast that they approach the mathematical concept of infinity while remaining technically finite. The space between the scattered white dwarf remnants has expanded to dimensions where the curvature of space-time becomes negligible on all but the largest scales, creating regions of nearly perfect flatness where the geometry of space approaches the idealized structures of pure mathematics. The gravitational fields of individual white dwarfs create tiny perturbations in this cosmic geometry, islands of curvature in an ocean of mathematical perfection. The quantum vacuum that fills this vast space exhibits properties that become apparent only in the absence of all other energy sources and material structures. The zero-point fluctuations that characterize empty space, according to quantum field theory, represent the last active processes in a universe that has otherwise achieved complete thermal equilibrium. These quantum fluctuations create virtual particles that briefly emerge from and return to the vacuum, maintaining a subtle activity that ensures the universe never reaches absolute stasis. The information content of the universe during this epoch becomes encoded primarily in the quantum correlations between different regions of space and the positions of the remaining white dwarf stars in the vast cosmic geometry. The holographic principle suggests that all information about the universe's history and structure is preserved on the cosmic horizons that bound the observable regions around each remaining stellar remnant. The consciousness that contemplates this ultimate cosmic state finds in it not emptiness, but fullness, the recognition that the universe has achieved its maximum possible information, content, and entropy while maintaining the mathematical line, structures, and physical laws that govern all natural processes. The cosmos becomes a completed work of art, a finished symphony where every note has been played and every theme has been fully developed. The white dwarf stars serve as cosmic meditation objects in this final epoch, their crystalline perfection representing the universe's ultimate achievement in organizing matter into stable, mathematically elegant structures. The carbon and oxygen lattices within their cores embody the same geometric principles that govern crystal formation on microscopic scales, extended to encompass the mass of entire stars in three-dimensional arrays of perfect mathematical beauty. The silence that characterizes this cosmic epoch is not empty, but pregnant with infinite potential. containing within it all possible quantum fluctuations and virtual processes that maintain the fundamental activity required by quantum mechanics. This silence represents the universe's achievement of perfect peace, not the absence of all activity, but the presence of perfect balance between all possible forms of activity. The eternal nature of this cosmic state emerges from the recognition that the universe has reached a configuration of maximum entropy that cannot be exceeded, a state of perfect equilibrium that can persist indefinitely without further evolution toward greater disorder. Time continues to flow, but without the energy gradients that drive irreversible change. Temporal progression becomes a pure mathematical parameter rather than a measure of physical evolution. The beauty of this ultimate cosmic state lies in its mathematical perfection, its achievement of the theoretical limits imposed by quantum mechanics and general relativity on the organization of matter and energy in space-time. The universe becomes a living demonstration of the mathematical principles that govern physical reality, a cosmic proof of the deep connections between consciousness, mathematics, and the fundamental structure of existence. The memory of all previous cosmic evolution becomes preserved in the quantum correlations and information patterns that characterize the final state, ensuring that nothing of significance is lost, even as the universe achieves complete thermal equilibrium. The history of stellar birth and death, galactic evolution, and the development of complexity and consciousness becomes encoded in the mathematical structure of the final cosmic configuration. The meditation on this ultimate cosmic peace provides profound comfort in the recognition that the universe's journey toward maximum entropy represents not a failure or ending, but the successful completion of a vast cosmic project. Exploration of all possible configurations of matter and energy within the constraints imposed by natural law. The cosmos achieves its purpose not through permanent preservation of any particular structure, but through the complete exploration of all possible structures. The consciousness that rests in contemplation of this cosmic completion finds in it a perfect mirror for the deepest qualities of awareness itself. The recognition that consciousness, like the universe, achieves its highest expression not through clinging to particular contents, but through the complete openness that allows all possibilities to arise and pass away within the unchanging space of pure awareness. Now, rest in this cosmic peace, where the universe has completed its long journey toward perfect equilibrium, where consciousness merges with the mathematical harmony that underlies all existence, where the final vigil of the last stars gives way to eternal rest in the infinite stillness of completed time. Sleep now in the embrace of cosmic completion, where white dwarf embers fade into perfect darkness, where consciousness dissolves into the pure mathematics of existence, where time itself comes to rest in the eternal now of maximum entropy, in the perfect peace that encompasses all possible states while remaining forever at rest, in the infinite silence that contains all sound, in the absolute darkness that holds all light, in the ultimate cold that encompasses all warmth forever and ever and ever. Amen.